This video goes through the geometric interpretation of simultaneous linear equations with two variables, so in 2 dimensions. Now make sure you watch that intro video first because it's really important to be able to visualize what's happening, and it's extremely important to understand what we're doing with 2 variables before getting to 3 variables and 3 dimensions. So spend that time and make sure you understand that first. Now if we have systems of linear equations with 2 variables, that means we have a1x plus b1y equals c1 for one equation, a2x plus b2y equals c2 for the other equation. So that's 2 linear lines. And our result from that is we can have one solution where the 2 lines intersect, so that's called consistent, or we can have an inconsistent system where there is no solution. So we all understand where 2 lines meet, they intersect, we have one solution. No solutions, you've dealt with parallel lines in the past. So if you've got 2 parallel lines, they don't intersect, so you have no solution. One that you may not have encountered before is infinitely many solutions, and that's where the 2 lines are actually coincident. So they are the same line, basically. Parallel and coincident lines are essentially the same line. So same y-intercept and same gradient. So let's look at an example. Solve the following equations by using matrices and interpret the system geometrically. So I am going to use inverse matrices to do this. We have also learnt Gaussian elimination. So our A, our coefficient matrix, our variable matrix, and our constant matrix. So now we go into solving. We have AX equals B. We need to pre-multiply to get rid of A on the left-hand side, so we do the same on the right. Inverse of A times A is the identity matrix. The identity matrix times by X is just X. So now we can solve. So that means we have the inverse of A times by B. Now to do the inverse of A, we need the determinant. So the determinant of A is 2 times 6 minus 3 times 4. So that's 12 minus 12, which is 0. Now, because the determinant equals 0, that means A is singular. That means there's no solution or infinitely many solutions. So in this case, we're looking at our inconsistent system. So now we have to work out, well, why isn't there a solution? Is it because the lines are parallel, or is it because they're the same line? So if we come back to my equations, 2x plus 3y equals 6, 4x plus 6y equals 24. First thing I'd look at is there a common multiple between the 2 equations such that they could be the same? I can't see that, so now I'm going to rearrange for y. So we have 6 minus 2x, so y is going to be 6 over 3 minus 2x over 3. So that's 2 minus 2x over 3. So our gradient is negative 2 over 3. Rearrange our second equation. So we get 24 minus 4x. Divide everything by 6. So that becomes 4 minus 2 over 3x. So my second gradient is also negative 2 over 3. So therefore, the 2 lines have the same gradient and are therefore parallel. And that's why there is no solution. And so the key is you can see that that gradient is the same in both lines. So that's one form of inconsistent solution. Let's look at another example. This one says Solve the following equations by using matrices and interpret the solution geometrically. Describe these solutions through the use of a parameter. Okay, so let's set up our matrices. A is going to be 2, 3, 4, 6. X, our variable matrix, X, Y. And our B is 6, 12. So our solution, AX equals B, pre-multiply. IX equals the inverse of AB, so X is the inverse of A times B. That gives us 2, 3, 4, 6 to the negative 1 times 6, 12. Now the determinant of A is 2 times 6 minus 3 times 4, which is 12 minus 12, which is 0. So therefore, A is singular and there's no solution. So now we have to go, well, why isn't there a solution? We can have lines parallel or lines are the same. So let's look at the two equations. 2x plus 3y equals 6 and 4x plus 6y equals 12. Now, if you look at the corresponding coefficients and look at the constants, what you should see is that the second equation is just the first equation times by 2. So if I label that 1 and 2, 2 is equal to equation 1 times 2. So that means the two lines coincide, which means the solutions are all points on the line. So there are infinitely many solutions. Now the second part of the question said, describe these solutions through use of a parameter. So if we use a third variable, lambda as the parameter, let's let y equal lambda. So equation 1 can be rewritten as 2x plus 3 lots of lambda equals 6. Rearranging for x, because we already know that y is equal to lambda, we want to know what x is. 2x is going to be 6 minus 3 lambda. So x is 6 minus 3 lambda over 2. So therefore we can write the solutions as x equals 6 minus 3 lambda over 2 and y equals lambda, and that's for lambda is an element of the real number system. Now this is called the parametric description of the line. Now using your calculator, use linear solving application. So go into your calculator, follow these instructions, and what you'll see is it comes up with that parameter as C1. So that there is lambda. And then you have lambda there. So that for the previous example is saying we have 3 minus 3 lambda over 2 as x, and that y equals lambda. Note that in the previous example, we had 6 minus 3 lambda all over 2, which is the same thing because 6 divided by 2 is your 3.